Welcome today to JPSD's first webinar, which we are proudly basing on the 2022 Solar Fuels Roadmap, which is to be published early next year. Today we're going to be offering somewhat of a trailer for this roadmap. So I'm going to... We're excited today to offer a stellar lineup of speakers with Professors Harry Atwater, Daniel Nasera, and Paul McIntyre giving talks, all of whom are authors on the roadmap. This will be followed by a panel discussion with Frances Houle, Roel van der Krol, and Paul McIntyre, and will be moderated by Gideon Segev. Before we start, if I could direct your attention to the link in the chat function, which will take you to the Slido for this webinar. Here you can post all your questions and you can vote for your favorite question also. And during the course of the webinar, we'll be trying to answer some of those questions. So I'm going to hand over to Frances Houle, who will be chairing today's speaker session. Dr. Frances Houle is a senior staff scientist in the Chemical Sciences Division at Lawrence Berkeley National Laboratory and Deputy Director for Liquid Sun Alliance, also known as LISA. She's also one of the 3 lead authors on the aforementioned roadmap. So, Frances, over to you.
Great, thank you so much, and welcome everyone. Thank you for joining today. I'm going to introduce our speakers without too much ado because I want to be sure to give them as much time on the program as possible. Our speakers are Professor Harry Atwater, Professor Daniel Nasera, and Professor Paul McIntyre. And first up, we have Harry Atwater. So Harry Atwater is the Otis Booth Leadership Chair of the Division of Engineering and Applied Science at CALTECH, and Howard Hughes Professor of Applied Physics and Material Science. He also serves currently as a director of the Liquid Sunlight Alliance, which is one of the projects in the DOE's Fuels from Sunlight Hub. And the title of his talk is Nanostructures for Light Management in Solar Fuels and Photoelectric Chemistry.
Okay, yeah, good morning. Thank you for the introduction, Frances. And I'm going to share. Can you see my slides, Tom?
Yes.
Or Frances. Okay, good. All right. So yeah, I was this morning. There are many aspects about photoelectric chemistry that pertain to solar fuels, and I was asked to address the subject of light management and particularly the role of nanostructures. So this is work that was done in conjunction with Sophia Cheng. And this is described in the roadmap, part of Sophia's PhD thesis. She's now an independent investigator at a new position in Taiwan. And so to begin with, in a photoelectrochemical system, almost all efficient systems comprise tandem photoelectrodes. So we can think then about the carrier transfer between quasi-Fermi levels for electrons at the cathode side, where electrons undergo interfacial electron transfer to a catalytic center, and holes on the anode side, which give rise to water oxidation. And so from the point of view of a photoelectrode, we're interested in high absorption and making our catalyst not absorb or reflect any of the light, and that's actually often a challenge. And we also want to have a tailored interface for electron transfer and low overpotential catalysts. And so if we can do all of those things, that goes a long way towards enabling high efficiency for solar fuels generators. And so there are a number of things that come into play. I'll say just a few about them. They're described in the roadmap about how we can use nanostructures to enable broadband absorption in very small amounts of semiconductor material. Say a few words about tailoring the optical properties of a record efficiency device for photoelectrochemical water splitting, and a little bit about how to generate transparency in opaque catalytic layers. And so to begin with, I can just note that in many cases we can use photoelectrodes of semiconductor materials that, when they're formed into nanostructured form, this gives rise to light matter interaction that leads to resonant modes. And so we have wires. You can think about these like organ pipes, and each wire diameter corresponds to a pipe of different pitch. And if we add up organ types that are at different tones, we can generate optical absorption where there are individual resonances denoted by these peaks here, such that a multi-resonant array can span the entire solar spectrum up to the band edge of the absorption of the semiconductor, in this case indium phosphide. And this just shows some experimental results for a patterned indium phosphide array where we're able to essentially get in a nanowire array near the limiting photocurrent in a nanowire array, whereas the planar equivalent thickness material of indium phosphide has about half the photocurrent. So that's an example of how nanostructures could be used to enhance absorption. So I'll just now move on to describe work on this device, which was a tandem device with a tandem photoelectrode whose band gaps were tailored to span the solar spectrum and just produce the photovoltage needed for photoelectric chemical water splitting using a rhodium hydrogen evolution catalyst and a ruthenium oxide water oxidation catalyst. And this between 2015 and 2020, we saw a rapid rise in the record efficiencies for photoelectric chemical water splitting, and this device achieved a efficiency, solar to hydrogen efficiency of 19.3%. So how did it do it? So it began with the use of rhodium nanoparticles, and the rhodium nanoparticles were produced by electrochemical deposition. And in this very small size regime, where mean particle size in the range between 10 and 15 nanometers, particles actually give rise to, small particles give rise to, their extinction is dominated by absorption rather than scattering. And it so happens for rhodium particles, they exhibit a plasmon resonance in the ultraviolet, but at this particle size and for rhodium, there is essentially negligible absorption in the visible frequency range. So this is quite interesting. It leads to a condition, if we look at the reflectivity of the tandem photoelectrode, we see that the reflectivity of a tandem photoelectrode decorated with catalyst, rhodium catalyst, which is enough catalyst to keep up with the catalytic turnover dictated by the photocurrent density under one sun, then the reflectivity here is equivalent to that without a catalyst, which is a way of showing that this catalyst is effectively transparent across the visible spectrum. This catalyst is supported on a titanium dioxide protective coating, and its thickness is tailored to be an anti-reflective coating. Also, this coating smooths out the spikes in the semiconductor band edge that would otherwise present effectively a resistance to electron transfer to the rhodium HER catalyst on the surface. So it has this interfacial layer of titanium dioxide plays a role as a protective coating and AR coating, and also smoothing out the band alignment in the tandem photoelectrode. So I'll just say before I turn over the mic to the other panelists that we can also use optical resonances in dielectric structures to enable substantially opaque metallic catalyst layers. So in this case, we're interested in looking at metallic catalysts for hydrogen evolution. And if I simply coat a surface with a metallic catalyst, will generate a layer that's substantially opaque. The question is, could I actually render that to be mainly transparent? And you can do that, for example, by producing nanostructures of titanium dioxide that enable resonant resonant waveguiding. So you can view this as essentially a broadband waveguide. And we can see here, for example, the reflectance of this structure. It acts like a beautiful AR coating, and it has a very high transmittance if I, for example, use a opaque nickel film. If I use just a nickel film without the nanocones, you can see here the reflectance is quite high. So effectively, these waveguides tailor the light coupling into the photoelectrode. And this shows essentially what the optical modes look like. You can see here across the visible spectrum, the evidence of transmission in electromagnetic simulations through these optical dielectric nanocones that tailor optical transmission, shown at each of these resonant transmission points. So there are multiple resonances in a cone-like structure, each resonance happening at a different cross-section of the cone, giving rise to essentially a broadband resonant transmission. So this is what the structures look like when they were fabricated with titanium dioxide. We tested these and showed that, for example, the nanocones showed, in fact, in experiment, reflectivity results and transmittance that was very similar to that in the predictions. This was also used in an OER photoanode application here, where silicon was used as a photoanode, and using a nickel film, nickel titanium dioxide silicon coated photoanode for OER. And in this case, the photoanode performed in such a way to produce a photocurrent density during OER that was indistinguishable from the photocurrent density for just a bare flat silicon photoelectrode. So that's basically what I wanted to share with you today, and and there are many more other things in the roadmap itself about use of photonic nanostructures for photoelectrochemical light management. So I'll turn it back over to you, Tom.
I'm Tom.
Frances. Okay, yes, sorry.
No worries. Thank you so much, Harry. That was really quite interesting. I'd like to remind all of the participants that there's a link in the chat to Slido, which is where questions should be posted. And I actually have one that is prompted by your by the flow that you kind of went through pretty quickly of how you make these structures. I was wondering if you can comment a little bit on how well nanostructures for light management can be mass produced. Is this something that is—
That's a good point. I thought about adding some slides about this. Let me just say that there are a number of ways to do this that don't involve direct lithography. Of course, direct lithography wouldn't be scalable. One is by nanoimprint technology, which has been demonstrated at the square meter scale. There are commercial printing systems for printing nanostructures this way once you have a master. Another is to use colloidal. So for example, the nanocone structure that I showed was printed in the lab using lithography, but alternative methods using, for example, colloidal particles as a lithographic mask can be demonstrated in a large area. So I think, you know, this is always a question when you use nanostructures. Of course, the rhodium particles are formed just by electrodeposition. There's no lithography involved. So it's just a matter of controlling the deposition process. But, you know, in a scalable application, of course, we're not going to use directly lithography.
Mm-hmm. So I see, I actually have a quick follow-up question, and then we can move on to Professor Nasera. How defect tolerant are these nanostructures for optical purposes?
Yeah, I think so. One of the experiences we had, for example, with these cone-like structures for broadband light absorption and light transmission, when you're trying to make a cylinder, it's actually very difficult to make a cylinder. It's much easier to make a cone when you're forming them by some etching process. Mm-hmm. The structures, if you're enabling broadband light absorption, if, for example, you end up creating a structure that excites optical modes beyond the band gap, that doesn't do any harm. It just simply is, you know, sort of potential for the nanostructure that's unused. So if you like, the process window for these is not terribly critical, I would say.
Which is very good news, I think, for those of us who think about process windows, for sure. Thank you so much, Harry. I really appreciate it. So I think we are ready now to move on to Professor Nasera. I'm very pleased to introduce Daniel Nasera. He is the Patterson-Rockwood Professor of Energy in the Department of Chemistry and Chemical Biology at Harvard University. And today he's going to talk to us about comparing artificial and natural photosynthesis, bioconcepts, and hybrid systems.
Okay, thank you, Frances. And I'm doing this on behalf of my co-authors, Leif Hammerstrom at Uppsala and Jenny Zahn at University of Cambridge. And photosynthesis, as we all know, uses sunlight, air, and water, carbon dioxide from air to make biomass and sugars and fuels. You can do that. What most people forget about photosynthesis is it's a two-step reaction. And photosynthesis didn't try to make CO2 from water directly. It uses light only to split water to make oxygen and hydrogen, nature's form of hydrogen is NADPH. In the dark, it combines the hydrogen with CO2 to make biomass. And that's an important concept for the biohybrid approach. The reason for separating and only using light for water splitting, it's just freshman science. The water splitting reactions thermodynamically uphill. Once you have hydrogen, and here I'm just keeping hydrogen separated in protons and electrons, its reduction of CO2 is thermoneutral or downhill for almost any carbon product or fuel you can think of. And so if you have a downhill reaction, you need not be using energy for that. As a matter of fact, you don't want to be using any energy. And you want to use all of the energy for water splitting. Now, in nature, in photosystem 1 and 2, you just saw a talk where you saw tandem photovoltaic, and you would look at this, and this is a lousy tandem photovoltaic because the two bands are overlapping each other. And so there's a huge efficiency loss up front for doing solar storage. I'm going to emphasize that in a minute. So that the maximum theoretical efficiency is 10.5%. In storage, most photosynthetic organisms store the best at 1%, most at 0.5% or 0.1%. One thing I hear commonly is that photosynthesis is inefficient. Absolutely not. The reason why this is overlaid is the organism is trying to live, just like you eat food and try not to store it. The same with this living organism. And unfortunately, photosynthesis wasn't told 3 billion years ago it needed to save us from being negligent societally and become our fuel source. So photosynthesis uses energy in a magnificent way to live, but it doesn't store it, just like you don't like to store it. And so that's where you can buy a lot of efficiency in storage, is in this light reaction. And that's where you use the inorganic part of the hybrid. And then in the dark reaction, you can use all the power of biology to run the thermodynamically thermoneutral or downhill reactions in the dark. And that's the basic concept of a hybrid, is to separate function just the way photosynthesis does. Now, the advantage of the biology piece is you can manage massive numbers of electrons and protons. So here's some fuels I put up. Formate, 2 protons, 2 electrons. So most CO2 reduction chemically deals with a small number of protons and electrons in C1 products. But look what happens when you get to ethanol, 8 protons, 8 electrons, isopropanol, gasoline, 50 protons, 50 electrons. So chemistry and chemical means aren't adapted to handling that many protons and electrons. Also, you need to make carbon-carbon bond formation. You just saw there's another Nobel Prize for making a carbon-carbon bond. So it says chemistry isn't very good at it if we're giving Nobel Prizes. Biology's expert. And there's high selectivity. Within a 10 kcal window, I could put hundreds of fuel-forming reactions. And nature can do that selectively. So managing protons and electrons without hydrogen, making CC bonds and doing it selectively is the power of the biological piece of the hybrid. You'll use the inorganic chemistry, and you just heard a talk that we can then use the high efficiency for water splitting on the solar part. So in the roadmap, there were 3 subcategories presented on hybrids: biomimetics, proteins, and enzymes and living systems. The biomimetic is literally trying to mimic the active sites of biology in a beaker. What's good about that is it gives mechanistic detail. It also, and I think this is another big advantage, is it engages a large part of the community in energy research. What's bad about it, and you shouldn't just think molecules, you can think of electrochemical CO2 reduction. It is unbelievably bad at carbon efficiency and energy efficiency. So I know there's a lot of papers in Science and Nature and everywhere that report record efficiencies, but you have to realize almost all the CO2 in those papers is going to making carbonate. And that's why it's not reported. It's not a Faradaic process. You're using electrons to reduce CO2. The detrimental reaction in CO2 reduction is hydroxide plus CO2. So all those papers you read, less than 1% of the carbon's going to a fuel. And worse yet, they have to work in concentrated base. And if you reach none of these papers report steady state conditions usually, so it's very bad energy efficiency. As a matter of fact, in some of the record papers that are published, you have to put 6 times the amount of energy into the system than what was stored to recover CO2 and get the hydroxide back. People flow hydroxide and use it as a sacrificial reagent. So there are real challenges here with the biomimetic approach. In the protein approach, what you do is interface proteins to your electron and proton source. And there, the beauty of that is you have enzymes that can work at very high turnover efficiencies. And it can be scalable. Also, since they aren't in a cell, you avoid downregulation. So the enzyme can just do its job, the reaction at hand. The problem and the biggest challenge confronting this system is that enzymes, once they're out of a cell, are fragile. And so it becomes a real issue of stability and maintaining the enzymatic system, which is running the dark reaction that's coupled to the water splitting light reaction of inorganic chemistry. And finally, there's the cellular approach, the living system. And that's where you pick up the stability, because the enzymes and proteins are stable within the cell, and then cells regrow. So basically you have an infinite living system. They also have natural carbon concentration pathways. And because of the power of synthetic biology, you can tailor carbon fluxes to lots of different products. The challenge here is you need to have what are called colony forming units. You need very, very dense cellular solutions to keep up with the rate you need to actually do, for instance, manufacturing. And what you have to do then is mitigate these downregulation pathways. Just to end, so 6 minutes. So I'll show you one advantage or one type of approach to these living systems. Here's the photosynthetic membrane, and I just mentioned the inorganic chemistry. This is what you heard from Professor Atwater. You can split water to make oxygen and hydrogen at high efficiencies. That allows me to offload almost the entire photosynthetic membrane from photosystem 1 and 2, because in photosystem 2 you make oxygen, photosystem 1 you make hydrogen, and it does it with this tandem overlap approach. So there you pick up a massive efficiency gain in the hybrid, but you still, once you have NADPH, then you need the dark chemistry. And there you use NADPH for 2 purposes. One is to provide hydrogen. I told you it was nature's hydrogen source. And also from NADPH, you make ATP. So in the energy that's stored in water splitting via NADPH, you convert the solar energy to cellular energy, ATP, via hydrogenase. So in the bracket, I can offload that system. I need to keep the rest of the system. And so what you can do, for instance, is here's a bacterium called Ralstonia eutropha. The way you interface hydrogen in the hybrid is you put a hydrogenase. Hydrogenases take H2 to protons and electrons, and then you can back end it to the biological machinery through synthetic biology to make NADPH. There's your hydrogen source and your cellular energy source, and then couple that to the carbon synthetic biology pathways that you desire to make sugars, fuels, chemicals, you name it. Here's one result. This one is pretty spectacular, and that Ralstonia eutropha, you can grow biomass. This is a true energy efficiency, sunlight into biomass. You weigh it and you calculate the energy in the biomass. So in this, you have everything: hydrogen solubility, the efficiency of the bio pathway. It's all there. This is a true efficiency. It's 11%. That's under concentrated CO2. Under aerobic CO2, it's 4.2%. And that's quite remarkable and points to this idea that you don't need carbon concentration mechanisms outside of the bug. That's a 2,500 difference in concentration between air and concentrated CO2. And you only have a factor of less than 4 in solar energy storage in a fuel. You can make solid things like polyhydroxybutyrate. You can even make liquid fuels. That one is isopentanol, the blue bar. That phase segregates with water. You can just pour it off. You don't need chemical engineers to separate it. You can also do other energy transformations that are important. Here, the previous system I showed you was only carbon fixing. So here you can do the same thing, use solar inorganic water splitting in the hybrid to make hydrogen, fix it as NADPH, breathe in CO2, and store now the fuel is stored internally in the organism, as say a polyhydroxybutyrate. And then that organism can draw on the polyhydroxybutyrate, pull the hydrogen out, and if it can fix nitrogen, it can use the hydrogen and fix it with nitrogen to make ammonia. It also makes a huge amount of ATP, and you need that for nitrogen fixation because it's extremely energy intensive, 16 ATPs. So most organisms downregulate nitrogen. They will get exhausted and die fixing it. Once you load them up internally with solar energy via CO2 and water splitting and then fixation to PHB, they have an infinite energy supply and they can fix ammonia at massive rates. So what you can do is do a 3-step reaction, do Harry Atwater water splitting, give hydrogen to CO2 in the bug to make polyhydroxybutyrate 2. Doesn't need to see the sun anymore. Put it in the ground, let it breathe nitrogen in, draw on PHB for energy and hydrogen and make fertilizer. So on the middle slide you have, and I'll show you why this is important for energy and climate in a minute. In the middle slide you have 100% fertilizer to grow lettuce and corn on a 400-acre farm. And that slide far right is 90% of the chemical fertilizer has been replaced with this bionic leaf biofertilizer. You get the same yield. What you should realize, by replacing that much chemical fertilizer, you save 170 pounds of nitrogen per acre. So on this farm, they use 130 pounds of nitrogen per acre. The way you make ammonia is by Haber-Bosch. You get your hydrogen from methane and you make a lot of CO2. So just on that farm trial I showed you, this is real data, on that 400-acre farm trial, you save by replacing 117 pounds of nitrogen per acre, you save 253,000 pounds of carbon dioxide from going in the air. After the bug eats the PHB, remember that carbon came from the air, it sequesters it. It sequests 29,000 pounds, sorry, you eliminate 22,025 pounds from Haber-Bosch, you sequester 29. So for that 400-acre farm trial, you save 253,000 pounds of carbon dioxide from going in the air. So that gives you sort of the feeling for the roadmap, the path of using hybrids. It sort of combines the best worlds of solar water splitting with the power of biology. And like I showed you, you can not only be better, but you can far exceed photosynthesis and then go beyond and actually impact climate change in a number of other different ways. So with that, I'm done, Frances. You can take any quick questions you would like to.
Yeah, thank you so much. That was really wonderful to hear about. I actually have one quick question, and that has to do with best ways to integrate inorganic artificial water splitting with the natural systems? You do it like in a separate place and
Yep. Yeah.
pipe everything over, or
That's a complicated question. So I don't want to get into all the detail. So some people try to use electrodes directly and shoot electrons into the organisms, say with nanowires. That's been shown not to be right. What happens is they want to run constant current, and they run at such high voltages they don't realize this. They're making hydrogen, and then there are these hydrogenators that are pulling the hydrogen in. There are other ways. People have used quantum dots and tried to eject electrons into the organism. That's now been shown wrong. It turns out you can remove the quantum dot. They were using cysteine as a decaking agent for their nanoparticles, and the bug was simply eating cysteine and turning it into acetate. So you've got to be really careful with this interface. The cleanest way is what I showed you, is using H2, or you use something like green methanol, for instance, Total is doing that, and then you feed it a C1 source. And I think at the end of the day, Francis, you're right. You do that over there and feed it. We've done both. We've integrated it directly and we fed it. It really depends on the application and the process you're doing. But you can make catalysts that are biocompatible with the organism or do a separate feed. And that all gets into the manufacturing, and what really gives you the highest cell densities, which is what you need, this 10 to the 10 to 10 to the 12 colony forming unit.
Yeah, great. Well, thank you very much. I appreciate the answer, and it's really very interesting talk. I'm going to move on now to our last speaker, who's Professor Paul McIntyre. Paul is the Rick and Melinda Reed Professor in the Materials Science and Engineering Department at Stanford University, as well as Professor of Photon Science and Director of the Stanford Synchrotron Radiation Light Source at the SLAC National Accelerator Light Source. The title of his talk is Photoelectrodes Based on Conventional Semiconductors, Silicons and 3/5, Protection Layers and Surface Functionalization. Thank you.
Great, thank you, Francis. Let me go ahead and share my screen. I hope you can see that.
Not yet.
Okay, let me see. How about that?
No, we're seeing Dan.
Yeah, we can see that now, Paul. Thank you very much.
All right, thank you. Sorry for the hitch there. So I'm presenting this on behalf of my co-authors on our contribution to the roadmap. Thomas Hanapel of the Technical University of Ilmenau and Shu Hu of Yale University. And it's my pleasure to be able to present today. I'm showing this background of water because, as you've heard in the previous two presentations, water splitting or oxidation of water is a critical element of any solar fuel approach because of its abundance as a source of protons and electrons for electrochemical synthesis of fuels and of other important chemical products. When we think about solar-driven water splitting, of course, there's an immediate association of the word solar with photovoltaic energy conversion using conventional semiconductors, because there's a substantial industry based around this, and that industry is dependent upon the properties of these conventional semiconductors, including their ability to efficiently absorb incident solar radiation. I'm showing here the fraction of the incoming solar radiance at the Earth's surface that various different materials will absorb, and silicon has remarkable ability as a light absorber, and it also, of course, like other conventional semiconductors, has very good carrier collection properties because of the long carrier diffusion lengths in silicon and 3/5 semiconductors compared to other semiconductor materials, including oxides that are frequently investigated for applications in solar fuels. So conventional semiconductors have these important properties. And in addition to that, there's the ability to leverage a tremendous amount of investment and technical development over many years in the growth of these materials and in doping and various other fabrication methods that allow for the formation of things like multi-junction photoelectric chemical devices. So what's pictured here is a schematic of the band gaps, the energy, the electronic structure and energy band diagrams of two different semiconductors materials, a 3,5 material, something with a band gap of around 1.7 eV, and silicon, which has a band gap of 1.1 eV, and how these can be coupled together by providing a tunnel junction between the two semiconductors, and then decorating the surfaces of the semiconductors with appropriate catalysts to bring electrons to the right side here for reduction of protons to make hydrogen, and holes to the left-hand side for oxygen evolution through the electrochemical splitting of water. What's also shown here are layers called anti-corrosion or passivation coatings, and this is one of the critical difficulties, however, of using conventional semiconductors is that their intrinsic lack of stability under the electrochemical conditions in which hydrogen can be synthesized through this kind of electrolysis process, and therefore the need for protective coatings. And this instability of materials like silicon or the 3,5s has been something that's been studied and reasonably well understood for many years. I'm showing here work by Heinz Gerischer from 4 or 5 decades ago, where the different possibilities with respect to stability of a N-type semiconductor that would be used in light-assisted water splitting is pictured in contact with various different kinds, with various different electrolytes exhibiting different redox levels associated with water oxidation, and for different cases with respect to the a tendency for decomposition of the semiconductor in contact with the electrolyte. So by understanding the nature of the electronic contact between the semiconductor and the electrolyte and its tendency for decomposition, one can look for semiconductors that avoid this problem. Unfortunately, for the conventional semiconductors like silicon or gallium arsenide, in fact, we see the unstable case is typical. So in terms of stabilizing the surface through other means, coatings is an obvious approach, and one particular approach that's gained considerable interest and has been shown to be quite widely applicable is using a technique called atomic layer deposition to coat the surface of otherwise unstable semiconductor materials and therefore to prevent them from exhibiting this kind of corrosion under water splitting conditions. So this is a schematic of the ALD process for deposition of TiO2 using a standard precursor, tetradimethylamido-titanium, and water vapor as the co-reactant. And ALD is effectively a form of chemical vapor deposition in which species are deposited through a chemisorption limited mechanism. This produces a very dense packing of adsorbed molecules on the surface during the pulsing of the TD-MAP precursor into the reactor. And then in a subsequent reaction step, the co-reactant, water vapor, reacts with the adsorbed precursor and produces something like a monolayer, usually somewhat less than a monolayer of TiO2. And this leaves behind a hydroxylated surface that is then an excellent surface for depositing TD-MAP on top of in the next cycle. So this is a process that can be done in a sequential way, and very quickly one builds up a closed and pinhole-free thin film on the order of a few nanometers in thickness. So because of this chemisorption limited deposition mechanism, the ability to deposit dense and closed layers at small thickness, it's an interesting approach for making corrosion-resistant coatings. TiO2 is one of the oxides that is stable according to Gerischer's rules for stability under water oxidation conditions, and we see for the TiO2 coated silicon sample shown here after many hours of testing that the structure of layers deposited an OER catalyst and iridium oxide catalyst, TiO2 protection layer, and the silicon substrate remains intact in this depth profile. But if the TiO2 is left out of the stack, we see a very significant oxidation of the surface of the silicon, and the iridium-based catalyst is actually exfoliated from the surface as a result of the growth of the oxide and the stresses that form. We've studied in a relatively small number of cases the mechanisms for the improved stability associated with TiO2 and the mechanisms for failure of these coatings in the cases where they do fail. And we find that actually the principal mechanism of failure is not oxidative attack of the underlying silicon. This is an experiment using isotopic tracers to characterize oxygen penetration into the structure. We don't find any evidence of oxygen tracer penetrating into the underlying layers and oxidizing the silicon during these experiments. However, we do find that other mechanisms often are observed, including loss of catalyst during the process of water oxidation, and that catalyst loss is often associated with features like the edge of a contact to the photoelectrode, where we see evidence of catalyst loss that appears as if it may be associated with cavitation from bubble formation. So more of a mechanical loss of catalyst material. So the mechanisms for protection and for those failures that do occur with these surface functionalized photoelectrodes are still a topic of investigation, and some of the interesting outstanding questions are associated with their failure and how to prevent or minimize it. The other point, the final point I wanted to make here is that by using these kinds of coatings and conventional semiconductors and combining them in appropriate ways, one can achieve, as has already been discussed by Professor Atwater, multi-junction devices of various kinds, devices that through various kinds of semiconductor structuring can achieve very high efficiency. I'm showing here a simple example of combining all silicon photovoltaics with an electrochemical flow cell and using ALD as a protective coating between the photocathode here, the silicon photocathode, and the electrolyte. With these kinds of approaches, it's possible to achieve a very stable operation, in fact, for many hundreds of hours, and relatively high solar to hydrogen efficiencies greater than 13% in this case. But there's this fundamental trade-off between efficiency and stability is manifest here in the sense that we have designed this kind of structure in such a way to avoid as many stability problems as possible. And in so doing, we've created something that really resembles a locally integrated version of a photovoltaic array and electrolysis. So one might ask, why not just do these things separately? Why integrate them together at all? One reason for doing this, I think, is that these integrated devices may find applications in off-the-grid local hydrogen synthesis because of their compact design and small footprint and the ability to use the same projected area of device for both electrochemistry and for photovoltaic energy conversion. But I think another exciting direction is to combine conventional semiconductors with catalysts in devices that are designed for use of solar concentration. So high levels of solar concentration allow efficient photoelectric chemical reactors to operate by optimizing light harvesting per unit device area. And they also leverage the heat that is generated and has to be removed from these devices through the flow of water through them to accelerate the kinetics of the electrochemical transformation of water to oxygen and hydrogen gaseous products. So I view this as an important additional part of the ultimate technology implementation of conventional semiconductors in the photoelectric chemistry field in efficient devices. And I should point out that this work is from Sophia Hausner's group at the EPFL, and she is a co-author of one of the contributions to the roadmap. So with that, I'll thank you for your attention and try to answer any questions you might have.
Great, thank you so much, Paul, for a really interesting talk. And of course, using the conventional semiconductors gives us all a fast on-ramp to getting the technology going out of the science part. There is a question for you from the audience, and it reads, when you add the protection layer, do you create additional surface states that act as electron traps, i.e. recombination states?
Yeah, it's an excellent question. And actually, this is one of the critical aspects of how of the design of these devices is how to manipulate the doping at the surface of the semiconductor and how to appropriately choose the protection material's electronic structure to minimize the effect that the person is asking about. That can be a significant problem if those things are not controlled very carefully. So we've put a lot of effort, as other groups have, into addressing that concern. And I think that it's to my mind, it is not a significant issue for the systems that I'm aware of, but it is something that we have to always bear in mind in the design of the protection layer.
And I had another question, and this goes back to something that Harry Atwater was talking about tolerant process windows. And I was wondering if you can comment on process window for deposition of these very thin protection layers.
Yeah. So I mean, this is really where I think the advantage of choosing materials that have already been developed and to some extent have been kind of road tested, if you will, in other applications is important. So in the case of atomic layer deposition, there's a relatively large number of materials now that are being deposited by ALD for various applications in industry, and therefore that we have a set of precursors that are of high chemical quality in the sense that they have very reproducible properties, and there's a relatively good understanding of how to use them in a pilot scale or even production scale environment, and there's a relatively good understanding of the ALD process conditions. What I have found is that there is, however, a lot of aspects of ALD chemistry that are relatively poorly studied because it's a technique that takes place at relatively high pressures compared to most vapor phase deposition methods. and there's a limited number of techniques to monitor what's happening with the chemistry in situ as a result of that. So I think there is, I would say the positive aspect is what I've said already, this significant experience with these processes and a large set of available precursors and a kind of a community of vendors who can make the chemistries and the equipment to do this. But there's also some of the basic reaction chemistry and the mechanisms that are still somewhat poorly understood and can sometimes lead to unexpected results.
Great. Well, thank you very much. I really appreciate that. There was actually one question for Harry that maybe you can answer quickly, Harry, if you're still on. Oh, excellent. This question is, I just need to know whether the phase of titania affects the overall performance in the nanocones that you were describing.
So we actually found some, I didn't go into the details, but the structure of these were actually titanium dioxide coatings that were prepared by atomic layer deposition, the method that Paul described. And we actually found that different precursors produce different microstructures of titanium dioxide. And so there's a lot of detail there, but for example, we used for those who are familiar with these, we used two chemical precursors, TD-MAT and something called T-tip, and these produce very different results. The ones that I showed were polycrystalline and rutile form, and showed much better stability than the precursors that deposited amorphous titanium dioxide films. Yeah, so there's a lot of subtlety. We actually found also, we did corrosion studies and found nucleation points for corrosion at microstructural defects in the polycrystalline films at lower density than in the amorphous films. Overall, I'll just sort of editorialize for a moment and say that I think at the state of the art right now is that we're able to produce, for example, water splitting and even CO2 reduction photoelectrodes that operate at pretty high efficiency. And if you think about this in the context of our proven solar energy technology, namely photovoltaics, we need to make things that last for 15 to 30 years, because you're making this big financial investment at the outset and you want to amortize it over a long time. And so this notion of focusing on durability is really important.
Thank you. Tom Miller, do we have time for one more quick question?
If it's a quick one, yeah.
Okay. We'll let Paul decide. This one is also for Paul. The surface functionalization is one factor. What other factors can be tested for the enhanced activity?
Enhanced activity. So in terms of the, I didn't show a lot of results on catalyst activity. I mean, in terms of the performance of the overall system, there are many, many things that go into that. Obviously, you want a corrosion protection layer that causes the minimal reduction in efficiency that's possible. But I think there's, in terms of the catalyst choice, structuring of the catalyst, the design of the semiconductor, if it's a multi-junction or a more complex semiconductor device on the photovoltaic side, that's critically important. Generally speaking, all of the things that we do in mating up photovoltaics with electrochemical devices has the potential for degrading or damaging the photovoltaic material. So that part of it has to be understood very well. And I think that that's also something that is quite specific to the technology that you're investigating. So I think one of the challenges we've had in this field is the lack of critical mass to address all of these things at the same time, which is often what's needed to really achieve stable and high system performance.
Thank you very much, Paul. So I'm going to turn this back over to Tom, and I thank all of our speakers again for great, very stimulating presentations and all of the time you took to answer the attendees' questions.
Thank you. Great. What a fab session has been so far. We've had some 3 fascinating talks, so really good. Before we go on to the next session, I just wanted to have a brief interlude to give you a bit more information about the roadmap. The 2022 Solar Fuels Roadmap is part of a program of roadmaps which are published in JFISD. These highly popular articles are broad multi-author pieces summarizing their fields and their future developments. In this case, this roadmap is led by Frances, Roel and Gideon and will consist of 17 two-page sections written by 42 authors, including everybody here today. So this is a great taster. Today's session is an excellent taster for the roadmap to come. And it will feature topics such as comparison of state-of-art catalysts for water splitting, carbon dioxide reduction, nitrogen reduction, and from materials discovery to functional photoelectrodes, and of course, including the 3 topics discussed today. So it's a very exciting roadmap and certainly one we're looking forward to publishing, and I hope you will enjoy reading when it's published. If you want to read other roadmaps on a wide range of other topics, such as UV emitters, plasma technology, materials by design, please go to this link here and you can read them all for free. Okay, now on to the next part, which is the panel discussion. Today's discussion will be moderated by Gideon Segev. Gideon is a lecturer in the school, senior lecturer in the School of Electrical Engineering at Tel Aviv University and a JFISD board member. He'll be joined by Frances Houle, Paul McIntyre, and Roel van der Krol. Since Frances and Paul have already been introduced, all that remains is for me to introduce Roel. Roel is the head of Institute of Solar Fuels at the Helmholtz-Zentrum Berlin for Material and Energy, and full professor at Chemistry Department of Technical University of Berlin. So I will now hand over to Gideon and thank everybody so far. Over to you guys.
Thank you very much, Tom. Thanks. So we've heard a lot about different challenges we have in the field of solar fuels, and so we're here to talk about some of them. Frances, the first question to you. So we have different challenges, and some of them will be very interdisciplinary. Now, let's say that you're now in the Department of Energy or the European Commission and so on, and you're issuing a call for a very, very big project that will require, several groups coming together. Mm-hmm. What kind of projects will you be looking for?
Well, to me, I think where we are in solar fuels now is we have a great basis in science as a result of many of the investments that have already been made. I would say on the engineering side, we're very much at the beginning. I would look for projects that blend science and engineering. I think it's really important that we have scientists and engineers working side by side. My experience in the private sector before I joined the National Laboratory is that you have to have that because often important basic science questions come up when you try to do the engineering properly. And it's only by people working together that you can really make progress. So these would be teams that would have chemists, physicists, material scientists, double E's, chemical engineers, electrochemical systems engineers, mechanical engineers, all working together.
Okay, great, thank you very much. So let's go from the broad DOE level of things to the one lab kind of work. Next question for you, Paul. Let's assume I'm looking to start my PhD or a postdoc, and I'm looking for the best opportunities in the field. Where do you see those? And let's look at this from both the basic science and the engineering point of view.
Yeah, that's a really great question. And I think I'll echo some of the comments that Frances just made and also some that Harry made in his presentation. So I think that from the perspective of a basic science postdoc, if I were somebody who wanted to have a fundamental impact on this field, notwithstanding the fact we have a pretty good science base for much of it, as Frances has said. I'll put on my hat here as a director of a scientific user facility and say that I think working on novel characterization of processes that occur at interfaces in these devices, I think this is an area where there's really still a lot of fundamental understanding that needs to be developed. And this is an inherently challenging problem because these are typically they're not stable surfaces. They're evolving as the catalyzed electrochemistry is being done on them, and they're evolving structurally, and there's obviously the surface chemistry is evolving, and it's in an aqueous electrolyte typically. It's a very challenging environment to probe these processes with the necessary spatial and energy and time resolutions that one would like to have. So I think any project that would allow me to do that, to take a piece of that and focus on some really critical step in the process of solar fuel synthesis at an active surface in a device, developing that methodology and taking advantage of it could have a huge impact scientifically. So that, to me, would be something to focus on as an experimentalist. Looking at more of the engineering side, I think this whole question of how do these devices actually fail, and what are the mechanisms responsible, and how is that dependent upon the system design and the various materials that are chosen. That's a critical problem from the point of view of this ultimately becoming a scalable technology. So that would be, to me, the engineering part of this that would be most exciting.
Okay, great. Thank you very much. Excellent. Roel, this one is for you. A lot of research is being done at addressing specific challenges. Let's take, for example, the activity of an electrode or the selectivity and so on. And in many cases, we see that addressing one challenge imposes another. For example, a topic that was raised earlier between nanostructuring and scalability of the system. Now, these come in several different ways. How do you address such trade-offs?
Yeah, the short answer, I guess, to that question is cost, right? And it's not so much cost of the device, it's cost of the hydrogen that you produce with that device in a practical application. That ultimately decides what you can afford to do, basically. And there is also important to keep in mind that solar cells are not nanostructures, right? There might be some surface texturing, but they're not nanostructures. And that's for a very good reason, because probably the gain that you have simply doesn't weigh up against the extra cost that you have to incur to make those kind of structures. I think when you start thinking about this, it's also important to try and understand why you increase the surface area, right? Is it because you need a large surface area to get an enhanced catalytic activity, or is it because you need to work on the trade-off between absorption depth and carrier diffusion length? So different reasons might require different nanostructuring approaches. So I would argue if you need to do something like where you really need lithography, as was mentioned and discussed between Frances and Harry Atwater earlier, probably you're out of luck, right? That's always going to be too expensive. But there's other ways and cheaper ways to nanostructures, and some of them you may be able to afford depending on the application. So if you have, let's say, a device like the ones that Sophia Hausner, for instance, is making with state-of-the-art 3-5 semiconductors in a solar concentrator arrangement, it's obvious that you can afford to spend a little bit more on the nanostructuring than when you use a 100 square meter panel-based array. So it's the cost that ultimately determines what you can afford.
Okay, great, thanks. The next question for all three of you. I'd love to hear your opinions on this. So we know that the semiconductor industry, for example, is very good at producing technology roadmaps. We know the Moore's law and so on. And so how do you see our field with respect to that? I mean, when will we be able to provide a roadmap that is for technology with clear guidelines for when we need to do reach whatever goals? Frances, do you want to go first?
Oh, sure. And I spent many years in the semiconductor industry, so I'm pretty familiar with how these things look. And I think it's never too early to start, to be honest. I think they are great tools for identifying what we know how to do and where we need a lot of work, as Paul pointed out, for interfacial management. That for success of any device, that has to be done. These are living documents, and so setting one up now doesn't hamstring the field for the next 20 years at all. It just is a tool to collect our thoughts and to identify priorities. And so my view is that we ought to start thinking about it yesterday.
Okay, Roel?
Yeah, I would argue one of the things I feel we're missing is some kind of reference design, right? I mean, very often we work on catalysts, either OER or HER, on the light absorbers, when we don't even know what component is the performance limiting element in the system that we're eventually going to design. So my fear always is a little bit that we spend a lot of time on, I don't know, and I just take a random example, right? Maybe we spend a lot of time on OER catalysts. Maybe we don't need to. Maybe the problem is elsewhere. We just don't know, right? So I think what the field needs is a handful of, let's say, architectures, device architectures, where we say, look, these architectures make sense from a chemical engineering point of view. And once we have that architecture, we can start calculating and thinking about the specific materials requirements that need to go in such a structure. Once we know the chemical engineering aspects, we know how good the catalyst has to be, what kind of overall potentials we can afford. Once we know the layout, we know how good the light absorbers need to be and what minimum carrier diffusion lengths we need. I think that's, I mean, there have, of course, been quite a few demonstrations of larger area devices, more and more, so that's great to see. But I don't think let's say, a conceptual design has emerged yet where everybody says, yeah, that would be a good structure. That will be something where we can really, join forces on and really work on that.
Good, thanks. Paul, what is your opinion on this?
I certainly resonate with what Roel just said. I think I'd point out further that one of the things that existed in the semiconductor industry before they even really started road mapping was a relative consensus about how to actually conduct relevant performance tests and to report that data. And that's sort of slowly emerging, I think, in the PEC community. On the endurance side, I don't think it's there yet. So often we're not really making valid comparisons from one lab to another or from one technology to another. And that makes it difficult to, in practice, create a roadmap, of course. The other thing I just point out about the International Technology Roadmap in Semiconductors, which is a very widely cited thing, that actually required also not just having a large number of people working on the technology and the science across many different institutions. It required companies making major investments and trying to figure out when they needed to make those investments based on where the technology was going to be at a particular time. And we don't have that critical element really yet. We don't have the people placing major financial bets that requires that same degree of rigor in developing a technology roadmap. So we need to kind of get there first, I think.
Can I say something? So I want to say I agree completely with what Roel and Paul said. They're totally completely right. I guess for me, I think about it as a strategic tool at this point, a strategy tool rather than a tactical tool. So the semiconductor industry got mature enough that it was purely tactical. So it lets you decide, we're going to use this tool versus that tool, or we're going to, prioritize this over that. I think we could use one as a strategic tool right now, just to even collect our thoughts and build the consensus that Paul just talked about, and build consensus also on devices. If we laid it all out and said, we need to make a decision to get from here to there, I think that will help prompt the conversation. So, you know, I think these points that Roel and Paul made were excellent points.
Great, thanks a lot. So let's talk about light a little bit. Roel, so people usually talk about light, you know, as a way to generate some photo voltage. Do you see other opportunities and advantages to coupling light to a photochemical system? Maybe something that's a bit different, like doing something special?
Yeah, I would argue the most obvious one is that light is also heat, right? When you talk about solar light. And I think in my mind, at least, one of the main, let's say, arguments for using this integrated photoelectrochemical approach over a decoupled PV electrolyzer approach is that you can make good use of this heat, right? I mean, because in a solar cell, you get the heat at exactly the wrong place, right? When a solar cell heat up, you lose in efficiency, and you need that heat at the point where you have the electrochemical reactions. So that's infrared photons, I would say, heat up the system, that's great, and it's automatically cooled by being in contact with water, so that's a no-brainer. I'd say on a more subtle side, I mean, you might be able to use light as a way to steer selectivity, right? There's these plasmonic effects, right? You can use plasmonics to steer the light where you want it to have, right? Where you want it to be or where you want it to end up. But you might also be able to use plasmonic effects to enhance fields in semiconductor and thereby enhance the absorption coefficient of these materials. Or you might be able to make optical excitations. For instance, if you think about a semiconductor surface and there's water there, right? So the semiconductor, if the water is chem-absorbed, you can make bonding and anti-bonding orbitals between the semiconductor and a water molecule, and you might be able to directly photo-excite such a bond, and that might give you some advantages in terms of selectivity of the reactions that you can drive. That, for instance, is something that I would love to see, and then there has been some initial studies where you can use the wavelength of light, for instance, to steer the selectivity of a photo-driven CO2 reduction reaction. That will be, I think, it's feasible, but it's not easy to demonstrate, and certainly not easy to make it efficient. But that's something I think where we also need to go and we need to think about.
Awesome, great, thanks a lot. So let's think of, about large systems. Let's assume, we're able to build large solar fuel facilities. So, Frances, what do you think would stand in the way of making such facilities, and what is the right size for them? For example, because if we do the math, we'll see that a hydrogen fueling station that's powered by solar power probably will not fit inside a city. So what is the right scale for these things, and exactly what's required to get there?
Yeah, this is, I think, one of the biggest challenges besides durability that the technology faces, to be honest. Excuse me. So one thing about solar fuels systems is that they can actually be deployed at many scales. They can be made small, relatively small, so they'd be little personal hydrogen sources for personal fuel cells instead of batteries, for example. So, or in a village where the demands were not high, all the way through to centralized facilities where you would be working at gigawatt scale. It's the gigawatt scale that is the problematic one, and to feed all of the hydrogen needs, for example, of the United States, I think requires the entire state of Nevada to be covered by panels, which is of course completely unacceptable. So I think that this is where we are going to have to start thinking a lot harder about the architectures and about right sizing. What is the correct size? What's the correct scale to work at? Right now, all the architectures are predicated on panels. Light is a very diffuse resource, and so it takes a lot of panels to capture enough light, and plus it's, light's only on for 8 hours or so of the day, and you only get the right kind of light in certain parts of the world. And so we need to be thinking a lot harder about how to use sunlight effectively, and also about how to if there are alternatives to the panel structure, which would immediately translate to using less land.
Okay, great. And another question along those lines, this one's for you, Paul. So in some cases, you see communities opposing large installations of solar fields and wind farms and so on. Can you imagine such issues with solar fuel facilities? And then from that perspective, what kind of design constraints would you put already right now in order to mitigate such opposition?
Yeah, it's a very interesting question. I think it depends to some extent on the pathway by which this technology actually matures to the point where it becomes a sort of a self-sustaining activity that will have substantial external industrial support. If that occurs via the kind of local use cases that Frances was talking about, sort of village scale or a remote military base or mining facility or something that's sort of off the grid, then I think there'll be substantial, practical concerns that have to be front of mind as these things are designed. In particular, most of the work that's reported in the literature uses concentrated acid or concentrated base as the electrolyte, and that's going to be I would say, very problematic in those kinds of applications. So I think it'll be necessary to be able to show results that are, high performance and efficiency and endurance under neutral pH conditions. I think that'll be very important. I think the other issues are more generic in terms of fuel storage and how to do that safely. That's something that's going to be an issue. If we're talking about hydrogen, that's going to be an issue more broadly, and I imagine that there'll be pretty widespread and inexpensive solutions for that part of it. But the electrolyte handling, I think, could be a significant issue.
Okay, thank you. Paul, earlier you mentioned a stage in which non-government organizations or companies start to put money and invest and become real stakeholders in the technology. When do you think the solar fuels field will be there, and what's required to get to be at that stage?
Yeah, I think it's likely that it's going to happen through these smaller scale demonstrations. I think it may be a little bit more like the development of fuel cell technology, where a lot of it came out of the space program and military programs, very specific use cases that allowed the development of the technology and ultimately its implementation at larger scale. So I suspect that there'll be some really compelling applications for remote generation of hydrogen with sunlight in an integrated system, small form factor that will be very important in driving this, and that will have to overcome some of the serious issues with endurance and reliability, and that based on that experience, a larger scale implementation will ultimately flow from that. So I'm not sure if we have that killer application yet identified, but I believe it's on the horizon.
Okay, thank you. Roel, next question for you. And I think this will be the last one before we take questions from the audience. We discussed several challenges, for example, scale up, efficiency, and stability. What do you think is required to meet these challenges? What do you think is the most urgent one? And where do you think the field will be after these challenges are solved?
There are still so many, right? I mean, we need transparent catalysts. We need good light absorbers that give large photovoltages, right? I do personally think we have quite a number of good OER and HER catalysts, so I'm less concerned about that. But of course, for the CO2 reduction, that's completely different. I would say if you think about one of the chapters in the roadmap also mentions sort of sets a minimum scale, right? And that minimum scale is like we need to be able to produce 1 kilogram of hydrogen per hour to be able to make a dent in this whole thing, right? If you think about that, if you have a 20% efficient solar to hydrogen efficiency, 20%, to make 1 kilogram of hydrogen per hour, you're going to need 82 square meters of panel, right? That's huge. So in my mind, and I certainly do agree with what Paul just said, right? We need a smaller area killer app somehow, right, to get it going. But ultimately, we're going to need something large. So in my mind, the biggest challenge is what I think we discussed before also, can we think of something that's scalable? So what Frances said in the beginning, we need to start really bringing the engineers together with the scientists and at least make sure, because you know, there's a lot of funding for hydrogen now in Germany, for instance. The government has promised 9 billion euros over 10 years for hydrogen-related activity. But even that, it's not unlimited, right? So we need to put our resources where they count, and they don't count if we start working or if we continue to work on problems that may not ultimately be a problem in a practical application. So I think it's really super urgent that we start to think about, you know, systems that produce hydrogen that can be scaled, and use that as a starting point to really start defining our scientific questions and the requirements that we have to fill. And that's actually, frankly, also what I think we need to make a real roadmap, because the roadmap project that we have right now is I would say a very nice collection of research challenges that we and other experts in the field see. But it's not a roadmap in the sense that you would have, for instance, a PV roadmap. Those look quite different with very specific demands, and we lack that specificity. That I think we need to bring into the system. And if we do that, to answer your question, where would the field be when it's solved? I would say if we do that, the field has the direction that we need. Because we're lacking a little bit direction, I think. Lots of activities, but scattered focus, and I think companies are smart, they know this, right? So it's traditionally quite difficult also to get companies to fund these kind of activities because they just don't see the application yet. So how can we expect them to see it if we don't see it ourselves? This is something we need to think about.
Yeah, very interesting. Thanks a lot, really. Thanks a lot for a great conversation. I think we answered actually the main questions we had coming from the audience. So I think it's back to you, Tom and Frances.
Okay, thank you very much, everybody. Thank you so much today. Yeah, okay, if we're coming to the end of this thing, this webinar, just all that remains for me today is really thank you to the speakers today for giving their excellent talks. I hope they give and the panelists as well, of course, who gave their very detailed knowledge about where the field is going. And I hope it's giving everybody today an excellent taster of what's to come when we publish this roadmap. As Roel mentioned, it's not quite like a industry technology roadmap. It really is a collection of experts in the field giving their thoughts about where the future direction of their individual topics are going. But it's nonetheless a really fascinating article, and I'm really looking forward to seeing it published in JPhysD. So, and thank you for Gideon, Frances and Roel for helping us pull it all together and bring everybody on board. It's really been a really excellent project to work on. So thank you. I think we'll end now and say good night to everybody. So thank you very much and good night.
Thank you very much. Good night.
Thanks.